Welcome back, all my students. Today we will be taking our chapter forward, our chapter Light, Reflection and Refraction. This is part 3. And in the last video, we have discussed about the sign convention for reflection by spherical mirrors. So see this, in this slide, I'll explain it once again. This is our concave mirror MN, and this is the x-axis, x dash and x. So what happens? Distance towards the left side. Anything towards the left of the mirror is taken as negative. So if an object is placed in front of the mirror, the object distance will always be negative for such an object. Height upwards, if any object is tall and height upwards, it will be positive. Height downwards will be negative. Okay, distance towards the right will be positive. Okay, that's why when we solve numericals related to light, we observe that the distance, object distance, is always negative because the object is always placed in front of the concave mirror. The object is always placed to the left of the mirror. So light from the object falls on the mirror from the left hand side. All distances parallel to the principal axis are measured from the pole of the mirror. All the distances measured to the right of the origin are taken as positive, while those measured to left of origin are taken as negative. Okay. Distances measured perpendicular to and above the principal axis along y-axis are taken as positive, and distances measured perpendicular to and below the principal axis are taken as negative. Okay. Now sign conventions are understood, and sign conventions are applied to both mirror formula, and it is used for solving the related numerical problems. Now let us see what is mirror formula. This is another important concept, the mirror formula and magnification. This is basically a formula which is used for calculations related to mirror calculations like concave and convex mirror. So let us start. In a spherical mirror, the distance of the object from its pole, this is the pole, so the distance of the object from its pole is called the object distance u. It is denoted by u. And the distance of the image from the pole of the mirror is called the image distance. Okay, so this is the image distance. The distance of the principal focus from the pole is called the focal length f. Okay, so all distances are measured from the pole. Distance of object from the pole is the object distance, and since the object will be placed in front of mirror, it will be negative. So object distance will be negative u. Distance of the image from the pole of the mirror is called the image distance, and it is denoted as v. Now this can be anywhere. Sometimes image is formed behind the mirror also, then it will be positive. In case it is in front of mirror, it will be negative. Now, the distance of the principal focus from the pole is called the focal length. This is the mirror formula. 1 by v plus 1 by u is 1 by f. This formula is valid in all situations for all spherical mirrors, for all positions of the object. Now let us go for magnification. What is magnification? Magnification, as the term implies, magnified, bigger than the usual size. Okay, so it is the enlargement of the image. An image is formed, it is enlarged. It is the enlargement of the image formed by spherical mirror relative to the size of the object. See, this is the object. The ray has hit here and it has gone here and like this. So an enlarged image is formed. An image formed is larger than the object size. So image size is larger than the object size. Let the image size be h, let the object size be h dash, or let the height of the object be h and the let height of the image be h dash. So magnification will always be the ratio. It will be the ratio of the height of the object image. Sorry, I'm extremely sorry. Magnification formula m is height of the image h dash and height of the object h. Okay, so m can be denoted as height of the image h dash and height of the object h. Now let us move forward and try to understand another formula for magnification. Magnification is also related to the object distance and image distance. It can be expressed as magnification m is h dash by h, that is minus of v by u. minus of image distance by u. So there are two formulas we need to remember. First formula is mirror formula. 1 by v plus 1 by u is 1 by f. Another concept is that of magnification. M is h dash by h, where h dash is the size of image, h is the size of object, is equal to minus v by u. V is the image distance and u is the object distance. The height of the object is taken as positive as the object is placed above principal axis. Height of image is taken as positive for virtual images and negative for the real images. A negative sign in value of magnification indicates that the image is real. A positive sign indicates that the image is virtual. Okay, so we have completed the part 1. Let us proceed to the part 2 of this chapter. Okay, yeah, light, reflection and refraction, part 2. So since we have understood everything about reflection, now let us try to understand what exactly is refraction. See, what happens is, it's a very simple phenomena. You can do one experiment. You can take a glass of water, you can put a pencil inside it. What you see is that the pencil, when it is seen from the air, looks different, and when it is gone into the water, it looks bent. Okay, so what has happened? Light has traveled from one medium to another. It has traveled from air to water. Light does not travel in same direction in all media. It appears that when traveling obliquely from one medium to another, the direction of propagation of light in the second medium changes. This phenomena is called refraction of light. Refraction is varied in different media such as kerosene, turpentine, transparent plastic slab, etc. Okay, see, in pencil it is like this. Pencil kept in water, it's like this. And if it is kept in different places, refraction is different. See, this is the incident ray. It has come in medium 1, medium 2 it has refracted. Okay, something like this. So understood? Let's move ahead. When a thick glass slab is placed over a printed matter, this is a thick glass slab placed over printed matter, we see refraction there as well. The letters appear raised. A pencil partly immersed in water in glass tumbler appears to be displaced at the interface of air and water. A lemon kept in water in a glass tumbler appears to be bigger than its actual size when viewed from the sides. Okay, now let's move ahead. There will be some experiments to demonstrate. There will always be some experiments to demonstrate the refraction of light. Okay, place a coin at the bottom of a bucket filled with water. Fill a bucket with water. Place a coin below it. With our eyes to a side above water, try to pick up the coin in one go. We will not succeed. What happens is reflected light coming from the submerged coin in water. Water is a denser medium, air is a rarer medium. Whenever light travels from a rarer medium to denser medium, we see that the ray of light will bend. Okay, so it has bent. So what is happening when we are trying to see, our eyesight is bent somewhere and we see the, something like we see the coin here, but the real coin is here. So we will not be able to pick the right coin at the right time. So reason, reflected light coming from the submerged coin in water on entering air bent away from normal due to refraction of light. Okay, due to refraction of light. An image size becomes larger than its actual size. Thus coin appears to be closer than its actual distance. This is one experiment to demonstrate the refraction of light. Place a large shallow ball on table and put a coin in it. Move away slowly from the ball. Stop when the coin just disappears from our sight. Ask our friend to pour water into a ball without disturbing the coin. Coin becomes visible again. This is because the coin appears slightly raised above its actual position due to refraction of light. Okay, now let us move ahead. Another experiment to demonstrate the refraction of light. Draw a thick straight line on white paper. Place a glass slab over the line such that one of its edge makes an angle with the line. Look at the portion of the line under the slab from the side. The line under the glass slab appears to be bent at the edges. This is a refraction of light. Place the glass slab normal to the line. Part of the line under the glass slab does not appear bent, it appears in straight line. So these are some different scenarios and experiments just which are used to demonstrate the refraction of light. There can be multiple. Now this experiment is important. This can be asked in exam. Refraction through a rectangular glass slab. This experiment is also done in colleges and schools to demonstrate the refraction of light. See what happens here. Take white paper drawing board, place a rectangular glass slab in its middle, draw the outline ABCD of the slab, fix two pins E and F vertically such that line joining pin is inclined to the edge AB. Look at the images at points this and this through opposite edge, fix two other pins. Okay. Remove the pin and slab, join the position of tip of the pins, produce a line. What happens is, I'll tell you, light travels from here. From air to glass. Air is rarer medium, glass is denser medium. We have a normal. What should have been the ray of light? It should have gone straight, but it doesn't go straight. The ray of light bends towards the normal in glass, and then while coming out, it is coming out of glass to air. Glass is denser, air is rarer, it again bends away from the normal. So this can be as the traced trajectory of the ray of light. Okay, fine. I hope it's understood. Let's move ahead. And what is the thing here? This is the normal. This is the angle of incidence. This is the angle of refraction. This is angle of incidence. This is angle of it is angle of refraction. Okay, let's move ahead. OO dash is the refracted ray. OO dash is the refracted ray. OH dash is the emergent ray. Okay, the emergent ray is parallel to the direction of incident ray. Refraction is due to change in the speed of light as it enters from one medium to another. Now, we have laws of reflection of light. Same way, for refraction also, few laws are there. They are equally important from exam point of view. It can be asked. So what is the first law? First law is the incident ray, the refracted ray, and the normal to the interface of two transparent media at the point of incidence all lie in the same plane. First is the incident ray, the refracted ray, and the normal to the interface of two transparent media at the point of incidence all lie in the same plane. Second law is also called as Snell's law of refraction. Snell was a scientist. What does the second law say? The ratio of sine of angle of incidence to the sine of angle of refraction is a constant for the light of given color and pair of media. This is also known as Snell's law of refraction. It is true for angle 0 to 90. Sin I by sin R is constant. This constant value is called the refractive index of the second media with respect to the first. And now let us try to define the refractive index. It is basically ratio of speed of light to that of the pair of media. It is used to measure the change in direction of light ray occurring in two media. Light travels faster in vacuum, 3 into 10 to the power 8 meter per second. In air there is only marginal decrease. It reduces considerably in glass or water. Consider a ray of light traveling from medium 1 into medium 2. Then the refractive index of medium 2 with respect to medium 1 is the ratio of speed of light in medium 1 and the speed of light in medium 2. So this is a very important formula. N21, N is the symbol of refractive index. N21 means that the refractive index of medium 2 with respect to medium 1. Okay, N21. What does N21 mean? N21 means the refractive index of medium 2 with respect to medium 1. It is denoted as speed of light in medium 1 divided by speed of light in medium 2, V1 by V2. Okay, so medium 1 is always air, medium 2 is glass. So what is the formula? The refractive index of glass with respect to air will be speed of light in air divided by the speed of light in glass. Okay. Refractive index of medium 1 with respect to medium 2 similarly will be represented as N1 by 2, and the formula will be speed of light in medium 2 divided by speed of light in medium 1, V2 by V1. Ratio of the speed of light in vacuum or air and in the medium 2, the ratio of the speed of light in vacuum or air, that is medium 1, and in the medium 2 is called the absolute refractive index. It is represented by N2. eta 2. If c is the speed of light in air and v is the speed of light in the medium, refractive index of medium and m is defined as speed of light in air by speed of light in the medium. We stop here.